Right, morning lads. Hope you're well. This is the last lesson before we break up for half term, and actually the last lesson of our materials unit. We will have an assessment on this in the first week back after half term, so I would like you to use a bit of your half term to do some revision for this unit. It's not a particularly long unit, and I appreciate we haven't had the chance to do the practicals yet. So hopefully, when you're back in, whenever that is, we'll get a chance to get ahead with the required practicals, which do form a really important part of this unit. Um, Today, we've got a short topic to do, and a lot of it is based on what we're doing in terms of keywords and something that you've looked at in GCSE before. So hopefully it should go pretty smoothly. What I'd like you to do to begin with, please, is pause the video at this point, and I'd like you to sketch a standard graph for stress against strain, standard axes, sorry. And I'd like you to sketch two lines on that axis. The first curve I want you to plot is one for a brittle material with a low tensile strength and a high stiffness. And then the second material I'd like you to look at is one with a high tensile strength and a low stiffness that is ductile. So pause the video at this stage and have a go at that. Okay, so I'd like to talk you through my thinking on this. So as normal for stress strain, our stress is always plotted on the y-axis, and that is newtons per meter squared, so pascals, as it's often written, and then strain. Remember, strain hasn't got any units because you're dividing a length by a length. It can sometimes be given a percentage, so don't worry if you see it like that. Sometimes it's just left blank. One of the few things that we come across which is dimensionless, having no units. So the first thing to look at is we're looking at A, so a curve for a brittle material. Now, the brittle material means that it's not going to have a long period of plastic deformation, sorry. So the majority of that graph is going to be a straight line. The low tensile strength part, this is short for the ultimate tensile strength that we looked at last lesson. And that effectively means that it's going to break without a great deal of stress being put on it. And finally, it's got a high stiffness. Now, what is the high stiffness telling you about the graph? It's telling you that it must have a steep gradient because you need to add a lot of stress to get a small amount of extension. So let's have a look at the first one. So this would be for A. It's got a low tensile strength but a high stiffness. So the majority of this graph is going to be a straight line. And that's your period of elastic deformation when it will return to its original length. And then it's going to have a very small period of plastic deformation before breaking at that point there. As we discussed before, the material that could represent is something like cast iron. The other thing to see is this second one. So we're looking at a ductile material with a high tensile strength with a low stiffness. Now, if the stiffness is low, as we mentioned before, it's the opposite to this. So for a small amount of stress, you're going to get a large amount of strain. The thing to be careful of here is it does, however, have a high tensile strength. So it does require a lot of force per unit area before it would break. So if we have a look at this, we're going to have a flatter line which goes to a much higher point. And then because it's a ductile material, we're also going to have a large or larger period of plastic deformation and an ultimate tensile strength there. Just a little bit of extra information on this. This section of the graph here, not to be confused with the necking region, which comes afterwards on these plots. This part of the graph is sometimes called work hardening. Not a term you'll be tested on in your A level, but if you do go into material science, it's something that you'll need to know about. So those are the two different graphs. Your key differences there: your gradient, lower stiffness, lower gradient; ductile versus brittle, short period of plastic deformation, large period of plastic deformation; and then finally your high tensile strength, signified by the higher breaking stress. So those are two key differences. Attached with this lesson, you'll see a practice exam question, and what this will require you to do is it'll present you with a graph for these different materials and ask you what is most suitable for a particular purpose. These are the sort of things that you need to be thinking about referring to. So ductile versus brittle, stress, tensile strength, and stiffness. It's quite a challenging exam question, but I'll upload a section on forms for you to fill in so I can have a look at your answers. So just try your best with that once you finish watching this video. Before I move on to the second part, which is this bit about alloys and density, I'd just like to think a bit about what gives materials these properties. We said last lesson that a material that's brittle like this is likely to be something like cast iron, and a material that's ductile, easily drawn into wires, is likely to be something like copper.